All right, guys. Let's get started. Can everyone hear me? Okay. Cool. All right. Hi everyone. I'm Li Jing. I'm very happy to be here today, and thanks for coming to the last session of the day. Today I'm going to talk about improving Pandas and PySpark interop with Apache Arrow. So, a little bit about me. I'm a software engineer working at 2 Sigma Investments. 2 Sigma Investments is a company based in New York. We're a technology company that applies data science in the field of finance, and we love Python. I recently become a Apache Arrow committer, which I will talk about a little bit about Apache Arrow later. I also work in the field of building data analysis tools, which I'm very passionate about. I also worked on other open source projects such as Flint, which is a time series library on Spark, and Cook, a fair scheduler on Mesos. So this talk will be more of a case study, a walkthrough of how do we improve an interop problem between Java and Python we found in PySpark, and how we use Apache Arrow to significantly improve the situation. This talk will briefly be a PySpark overview. How many of you guys have heard of PySpark? And how many of you guys use PySpark for research, for engineering? Awesome. So I can probably be a little bit quicker about that. Then I'm going to focus on a specific area of PySpark which I think need improvements, which is Python UDFs. Then I'm going to talk about Apache Arrow. What is it? Why it's interesting? Why you should care about it? And I will talk about improvements to PySpark UDF that we can make with Apache Arrow, and finish with future roadmaps. Sorry, this seems to. Hopefully, it's all good. All right. Let's talk about PySpark. So Apache Spark is a tool for, I think it's a tool for distributed data analysis. It's an Apache project, which makes it open source, which is great. And it's mostly a JVM-based technology, which means the core of Spark is running on JVM, but it comes with a Python interface called PySpark. Spark comes with different functionalities organized in different modules. There's a relational module that deals with join data, grouping data, some aggregation statistics. And there's Spark MLlib, which is a Spark module for stats and machine learning. And Spark also deals with streaming data. And why should you care about Spark? Why don't you just use Pandas and everything else along with it? Well, I think there's 2 reasons I found Spark very appealing to me and the problem we're facing at 2 Sigma. The first is Spark can deal with a bigger data than Pandas. Pandas is designed for something, I would say, along the range of 10 gigabytes memory, data set in memory. It works really great with this side of medium-sized data. But when you want to go out to, let's say, a terabyte of data, then it comes to struggle. It's no building support for that. And also, most of the algorithms in Pandas and NumPy, they're single-threaded. They're designed for running really fast on single core. However, Spark is more of a parallelism solution where it scale your computation based on how many cores you have. So whenever you find you want more parallelism, and if your data is too big to fit in the Pandas paradigm, then it might be interesting to look at something like Spark. Apologies again. Okay. Okay, I probably just need to be more gentle about that. So what is PySpark? PySpark is the Python interface for Spark. It mostly has 2 major. Excuse me. Can you actually help me with the connection here?
Let it reset.
Okay.
Just let it reset. Sometimes it's cutting out because of climate.
Okay. So as I was saying, Spark mostly has 2 major use cases. One is PySpark provides its API front end for the building Spark functions. The example here I give is you just want to compute +1 on a column. This line of code here is written in Python, but actually the computation itself has nothing to do with Python. The code actually is translated into Java code and running in the JVM. The second case here of PySpark is it provides an interface to run native Python code through this function called user-defined functions. Similarly, I'm giving the same computation here, but by using a UDF. Here, I'm doing +1 through a Python lambda function. And this code is actually going to be run on Python. The way it works is Spark will send the data from the Java JVM to a Python process, invoke this lambda function, and send the results back. And today, this talk is going to be mostly focusing on the second use case, which is UDFs. Now I'm going to talk about the current state and limitations of PySpark UDFs. Again, UDFs is PySpark's interface to interact with other Python libraries. We're going to focus on two types of UDFs here. One is row UDF and group UDF. Row UDF is just a very simple concept. It's a UDF that operates on a row-by-row basis. It's similar to a mapper operation. Examples here, people usually want to use row UDFs for something like string processing, maybe tokenize a string, or you want to do some timestamp processing, round a timestamp to some business days, etc. Row UDF is really simple to use, but it's pretty limited because it has not great performance. Usually we found row UDF is about 1 to 2 orders of magnitude slower than alternatives, which can be either a Spark building functions or a optimized Python vectorized operation. The second type of UDF is group UDF, which is UDF that operates on multiple rows. This is similar to a group by operator followed by a map operator. Examples here, you want to compute monthly with a main, or something that can be done after a group by. So this type of UDF is not supported out of the box. You can do it with Spark, but it's really hard to do it, as we'll see in a second. Also, it suffers from the similar poor performance issue as the row UDF. Here I'm going to give a quick example of I just want to calculate values following this formula. I want to subtract the mean and divide it by the standard deviation of the values, maybe by each month. And here's the code you have to write to do it in PySpark. Oops, even the screen doesn't like it. Yeah, the code is probably too bad. Even the screen kind of hates it. Anyway, you don't need to read the code, but the idea is to show you how complicated it is to perform this simple operation. And if we take a look at closer, 80% of the code is actually just boilerplate. You just need these 4 lines actually to express this computation. And the code is slow just because we have so many overhead in the creating these intermediate steps. So to summarize, we found there's 2 issues with the UDF in PySpark. First, because of it has this JVM and Python issue, and it has to move data between them to actually invoke the UDF. The data movement is actually pretty expensive because of the inefficiency. Also, the scalar computation model is just not great. Operating row by row is just not going to work if you have a lot of data. So how can we use something that can solve this problem? Now, Apache Arrow comes to rescue. So what is Apache Arrow? Apache Arrow is an in-memory columnar format. It's built on top of a successor packet. And it's open source standard from the start, which means it has developers from a lot of major open source projects getting involved in the design phase to make sure they all agree on the format and they think they can work for them. The benefit of introducing something like Arrow in the space of data analysis is it can share the effort and create an ecosystem. What is great about Python, I think, is basically every Python library knows how to deal with NumPy arrays and pandas data frames. And Apache Arrow is trying to solve this problem not just within Python, but across different languages. So the idea will be you have 2 systems, maybe one in Java, maybe one in Python, maybe something else in Julia or R, and you want to kind of use them in an integrated environment. And if they can all talk with each other using Apache Arrow, then the overhead is significantly reduced. Here's just another simple illustration of the idea. without Arrow, for each pair of system, if they want to talk to each other, they have to do, first the developer have to write specific code to convert the different format. And also, that code is probably not efficient enough because it involves a lot of copy and paste. The idea with Arrow is if everyone knows how to convert the data structure to Arrow, or better, if they can use Arrow internally as the data structure, then they can just talk to each other much easier. To give another taste, just to give a taste of what the Arrow data structure looks like, here I'm showing a person's records. So there are 2 records here, and each record has 3 columns. As you can see, they can be simple columns like string, integers, or they can be something more complicated like a nested of phone numbers, things like that. And on the right side, you can see how Arrow represents this in memory. It's actually very flat. For each of the columns, the values is actually stored in a flat array. And in order to present either the variable length or the nested data structure, Arrow adds on a few offset arrays on top of it. So it's really, as you can see, it's really easy to say if you want to flatten the phone numbers into a single array and do some aggregations or counting on it. It's really easy because the values is just already flattened. Here is just another kind of presentation of the Arrow data structure, but from a memory layout point of view. Do you have another cable, or that's it?
It's your hookup, man.
Oh, okay.
Yeah, it's your HDMI. Nobody's had this issue all day. Might be coming back. So I'm thinking that it's this, the actual.
I don't think I have. Do you have another type of?
It's weird. So weird. Hold on.
It's another screen, I think. Oh. Apologies again. This is the Arrow format from a memory point of view. The point of here is to show, actually these vectors are all just contiguous memory, contiguous byte blocks in memory. Actually, Arrow is organized into this idea of record batches. So a record batches can be, a few, let's say 5 columns with like 10,000 records. And for each record batches, it is just contiguous memory. It always comes with a data header, so you can jump into the specific columns you want very, very fast. And also these different value vectors can be accessed very efficiently using offsets. Arrow is really designed for high performance, which means it's designed for maximize the CPU throughput by using things like pipelining or SIMD or cache locality. Also, Arrow is great for scatter-gather I/O, which means you can write a single stream of I/O into multiple buffers very efficiently using just the OS operation. Finally, I want to show some results of the current applications of Arrow. You can read more in detail on the Arrow blog, but the idea is it's pretty performant in all cases. So now let's talk about improving PySpark UDFs using Arrow. How do we use this great technology to help the situation? So we did 2 things here. First thing is we vectorized the row UDFs. Again, to kind of remind ourselves, the way it currently works is you have one executed process, which is a JVM process, and you have a Python worker process. And upon executing this UDF, Spark will send rows from the executor to the Python worker in this pickle format. And upon receiving these rows, the Python worker will invoke this UDF, which is a row-based, so it's going to do this row by row on a for loop, and send the results back after it's done. This is super simple, but also, again, as we mentioned earlier, it's not very efficient. To further illustrate this, we took a profiling of executing this simple UDF lambda x plus 1 on PySpark using the existing UDFs. And there's a few things I want to talk about here. First is the overall throughput of computing the simple operations is kind of bad. It's only 8 megabytes per second. So it's bad by any standard for such simple computation. The second thing I want to highlight is actually we found over 90% of the running time is spent on the serialization and deserialization code. So a lot of overhead. So what we end up doing is we build 2 converters from the Spark executor to turn Spark rows to and from Arrow record batches. And across the wire, instead of sending these pickled rows, we send this immutable arrow batches. And upon receiving these batches, instead of applying the UDF on a row-by-row basis, now the Python worker can apply a vectorized UDF on each batch. So it's and send the results back afterwards. So this is the same benchmark results we did before and after the change. And before we'll see it takes about 4 seconds, and after it only takes less than 100 milliseconds. So it's a great speed up, first of all. And second of all, if we look a little bit closer, we can see all the overhead of serialization and deserialization are removed from the bottom version. You cannot find any of these overhead here. And last but not least, even the I/O part is more efficient. Because Arrow utilizes scatter-gather I/O, you end up having much less system calls to I/O calls and end up having much faster I/O. So the second improvement we made is improving the group UDFs. The way we did it is we introduced this group UDF on this function called group apply, which is a very simple notion. I'm sure you all know about it. Its a basic idea is to break a problem into smaller pieces, operate on each pieces independently, and put the piece back together. It's a common function supporting a lot of languages. Pandas, R, Spark, SQL, they all support that. So what we did here is we utilized the existing groupby and combine operators in Spark, and we just changed the apply step to support UDFs, which now the UDF takes a function from a Pandas data frame to another Pandas data frame. Just to go back to the slide, the UDF now is a transformation on the Pandas data frame. Here is just an illustration of what's happening under the hood. Spark organizes data in different blocks on different machines, and the groupby will trigger a shuffle phase, which sends the data to its correct group. And for each group, we can then we apply the UDF on each group and get the results back. Let's go back to our previous example of we want to run this simple computation on data breaking by month. And here's the code before and after. Before it's just terrible, a lot of overhead, and afterwards it's reasonably well. I wouldn't say it's perfect, but it's reasonably well, easy to understand, read and write. And the core, the major of the computation is just the middle one here, which is just the Pandas operation. So this API is actually, this slide is made a little bit earlier, so the API has changed since then. You can refer to either the PySpark docs or this blog link I have over here for the most up-to-date API. So finally, let's look at some quick performance comparisons. We run a few different computations and comparing them, comparing the row version versus the vectorized version, and we can see it's clearly the vectorized version is much better. We achieve anywhere from 3x speed up to 100x speed up depending on the computation, and we are quite happy about the results. So if you think this is interesting, if you have faced the same problem, you use Spark, you want to make PySpark integrate with Pandas a little bit better, you can try this out. This feature will be available in an upcoming Apache Spark release. And you can also try this today, actually, with the Databricks community version, which is a company that provides hosted Spark support. And you can try it for free. And I wrote this blog earlier to explain the work in more detail. So if you're interested, take a look. So finally, just some future roadmaps. Here's the Jira. This is a master Jira, covers all the issues with PySpark, Pandas interoperability. We have more things we want to do in the area. So you can watch it, vote it, comment if you want. And on the Arrow side, we're working really hard towards Arrow 1.0 release, which will make things much more stabilized. The APIs and the binary representation. Also, just to look forward to more Arrow integration. I think there's a lot of talks in PyData. There's a Dremio talk tomorrow about integrating Arrow with Dremio. There's probably some other work going on. So this mailing list, if you want to get involved, feel free to post anything here. Just the people I work with to make this happen. Very happy about that. With that, I'll finish my talk, and I'm happy to take questions. Go ahead, please. Yeah. The way PySpark works is Python always Spark always spins up this Python process for running UDFs, and unless it's UDFs, it actually doesn't need to start up the Python process. So it's purely for the purpose of evaluating UDFs. Go ahead.
How is the Arrow memory format different than Feather, or is it? I know that it has some type of relation. Do you know anything about that?
I cannot answer to the specific format of Feather because I'm not very familiar, but I think they kind of converge at some point. I think Feather is actually part of Arrow right now, or yeah, I think it's.
That's why I'm like confused on what the relationship is.
Yeah, it's.
The same thing.
Yeah, they probably just merged them at some point. Feather is for R, right?
It's for R.
Yeah. I think it gets. There's a blog. Wes McKinney, I think wrote a blog on that some time earlier about putting Feather into Arrow and some performance speed up after doing that, so you can check it out. Go ahead, please. There's some typecasting down. For this specific use case, the typecasting is down on the PyArrow side. So PyArrow has functions that you can cast a long to double or upcasting or downcasting. So it's purely down there. Is that a question? Go ahead, please.
Is there a mechanism for supporting libraries inside UDFs? Like you want to load a sidekick model that ran in
Yeah.
UDFs?
Yeah, the entire, I think a very important use case of UDFs is you can use any Python libraries with that, because you have this Python process running, and whatever the Python process has access to, you have it in your UDFs.
Okay, cool. Thank you.
Go ahead. Sorry, say again. How does
I mean, so it sounds like you're taking advantage of how Arrow is storing this data and then the
right?
Now, if I just load like a scikit learn or something, which doesn't know anything about that, but I can have to put what that format.
Arrow is So Arrow is actually zero copy to pandas. So if you do Arrow table.toPandas, it's zero copy. So it's basically like you can use any Python libraries with Arrow format, just because Arrow can get into pandas so easily. All right, thanks for coming again.